So let's now try to solve some complex equation. Let's try and solve z plus 2z bar, which is equal to 6 minus 4i. And let's try to solve this for z, right? So first thing we can do is we can let z to be equal to a plus bi. So if that is the case, I have a plus bi plus 2 times a minus bi is equal to 6 minus 4i. So this becomes, well, we have a plus 2a, we have 3a, we have bi minus 2bi, which is minus bi. This is equal to 6 minus 4i, right? So we have this equation here. Now both sides of this equation will be equal if and only if the real and imaginary parts of both sides are equal. So what we can do is we can equate the real parts together. So we have 3a, which is equal to 6. This is my real parts. And we will have the imaginary part minus b to be equal to the imaginary part on the right hand side, which is minus 4. So we can cancel out these negative signs. This will be b is equal to 4. So b is equal to 4. And on this side, the real part a is equal to 6 by 3, which is 2. Right? So z is equal to a plus bi. So we have z to be equal to 2 plus 4i. So this is our value of z. This is the solution to our complex equation here. Right. So now let's try to prove that z times its conjugate is equal to the magnitude of z squared for all complex numbers z. So for z that belongs to the set of all complex numbers, right? So we can just let z to be equal to a plus bi, and so then we can find z times its conjugate, which is a plus bi times a minus bi, right? And this becomes a squared plus b squared. So if I expand this, I will get a squared plus b squared, and I can also write this as the square root of a squared plus b squared. Sorry, square root of a squared plus b squared whole squared, right? And we know that this should be equal to just the magnitude of a plus bi squared, right? We've shown that the magnitude of z is equal to the square root of a squared plus b squared, where z is a plus bi, right? So this is just equal to the magnitude of z squared. So we have shown that z times its conjugate is equal to the magnitude squared. So we have just shown this. Now let's also try and prove that the magnitude of the product of z and w is equal to the magnitude of z times the magnitude of w for all complex numbers z and w. So z and w belong to the set of complex numbers, right? So we can let z to be equal to a plus bi, and we can let w to be equal to c plus di, right? So if I find the product of z and w first, I have a plus bi times c plus di, and if I expand this out without showing this explicitly, I should get ac minus bd plus ad plus bc I, right? Now if I take the magnitude of this, so I'm taking the magnitude of ac minus bd plus ad plus bci, and this will be equal to the square root of the square of my real part plus the imaginary part squared, right? So we have ac minus bd whole squared plus, so whole squared plus ad plus bc whole squared, right? So what I can do now is I can just expand this all out. If I expand this, I will get a squared c squared minus 2abcd plus b squared d squared plus a squared d squared plus 2abcd plus b squared c squared, right? And these terms, they cancel out. And if I factor out an a squared term, I will get c squared plus d squared plus b squared. So I'm factoring out a b squared term now. I have d squared plus c squared. And if I now factor out c squared plus d squared, I will get a squared plus b squared times c squared plus d squared. So I just factored out this term here. And now what I can do is I can split up this square root into two terms. So I have a squared plus b squared times square root of c squared plus d squared. And we should know what this is equal to. This will be just equal to the magnitude of a plus bi times the magnitude of c plus di, right? Which is equal to the magnitude of z times the magnitude of w, right? We showed that z is a plus bi and w is c plus di, right? So we started off with the magnitude of the product of these two complex numbers, and that is equal to the product of these two magnitudes, right? So the magnitude z times w is equal to the magnitude of z times magnitude of w. So we have just shown this. Right. Now, suppose that the magnitude of z and w is equal to 2, and the magnitude of z is equal to the magnitude of w, which is equal to 3, right? And we have to now find the magnitude of z minus w. So how can we do this? So there isn't a clear way to express this magnitude in terms of the magnitude z plus w, or the magnitude of z and magnitude of w. Instead, we can write this in terms of z, w, z bar, and w bar, right? So earlier we showed that z times z bar is equal to the magnitude of z squared. So using this relation, we can show that, the magnitude of z minus w squared is just equal to z minus w times z minus w, or the conjugate of this, right? And that will be equal to z minus w times z bar minus w bar. And if I expand this, I get z times z bar minus z times w bar minus w times z bar and plus w times w bar, right? And this becomes z bar, so the magnitude of z squared plus the magnitude of w squared, right? And in the equation, we have some information given, so let's keep this in mind. So since magnitude of z is equal to magnitude of w, which is equal to 3, then we can show that z times z bar, which is equal to magnitude of z squared, is equal to 9, right? We have just 3 squared. And w times w bar is equal to the magnitude of w squared, which is also equal to 9, right? So this becomes, so we have 9 plus 9, so we have 18 minus z w bar minus w z bar, right? And that is equal to the magnitude of this squared. And the other information that was given is we have z, the magnitude of z plus w, to be equal to 2. So that means that the magnitude of z plus w squared is equal to 4, right? So this is equal to z plus w times z plus w bar, and we can just write this as z bar plus w bar. And if I were to expand this, I would get z bar plus z times w bar plus w times z bar plus w times w bar, right? And this just becomes right, and we get 18 plus z times w bar plus w times z bar. 18 because this is 9 and this is 9, as we've shown over here, right? So now we can see that from the magnitude of the magnitude of z minus w squared, this was equal to 18, right, minus zw bar minus wz bar. I can write this as 18 minus this, right? And now we see that this is equal to 4, right? This was equal to 4. So from this I have w times z bar plus z times w bar to be equal to 4 minus 18, which gives us minus 14, right? This is minus 14. So I can now just substitute this here for the magnitude of z minus w squared. So I have 18 minus 14. This gives us 32, right? So from this I can then find, if I take the square root of both sides, the magnitude of z minus w will be equal to the square root of 32, which is 4 root 2, right? So this is my answer. Okay, so now let's try and find all the complex numbers such that, all the complex numbers z such that z squared is equal to 21 minus 20i. So to find all the complex numbers z such that z squared is equal to 21 minus 20i. Now you may initially try to take the square root on both sides to get something like this. This won't be helpful. This is not going to take us anywhere, right? Our square root function, this is our real valued function, and this is only defined for x to be larger than or equal to 0. So using this square root function, we cannot actually find a proper value for z, right? So what we can do instead is we can find complex numbers whose square is actually going to be equal to 21 minus 20i, right? So let's find complex numbers that if we square those complex numbers, we will get 21 minus 20i. So let z be equal to a plus bi. So then we will have a plus bi whole squared to be equal to 21 minus 20i. And if I expand this, I get a squared minus b squared plus 2abi. And this is equal to 21 minus 20i. Right. Now what can I do? I can equate the real parts of both sides and the imaginary parts of both sides. So this is obviously, so we know that a and b, they belong to the set of real numbers. So a squared minus b squared is something that is real, right? And this is our imaginary part. Similarly, this is our real part, this is our imaginary part. So let's equate those sides together. So we have a squared minus b squared to be equal to 21, and we have 2abi to be equal to minus 20i, right? So we can cancel out the i's. We have ab is equal to minus 10, and from this I can find an equation for b, and that will be equal to minus 10 by a. And I can just substitute this into this equation here. So I have a squared minus 10 by a squared, which is equal to 21. So this gives me a squared minus 100 over a squared, which is equal to 21, right? So if I multiply both sides by a squared, I get a to the power of 4 minus 21 equals to 21a squared, right? And this becomes a to the power of 4 minus 21a squared. So this should have been 100, my bad. This is 100 minus 100 to be equal to 0. So we are left with this equation. Now what we can do is we can write this equation in quadratic form, right? So we can let u to be equal to a squared. And if we do this, we have u squared minus 21u minus 100, right? So now we can try and factor out this equation, right? We can just factorize this equation. So what can we do? We can find two numbers that if I multiply them, I will get minus 100, and if I add them, I will get minus 21, right? So what are those two numbers? I can consider minus 25 times 4, that gives me minus 100, and minus 25 plus 4 gives me minus 21, right? So I will have u minus 25 times u plus 4 to be equal to 0, right? So from this, I can use the zero product rule to get u to be 25, u to be equal to minus 4, right? And if I substitute this back, I will have a squared to be equal to 25 and a squared to be equal to minus 4. And from this, I find a to be equal to plus or minus 2i. From this, I find a to be equal to plus or minus 5. Right, so these are the values of a that I can get. But we know that, right, so what did we start off with? We had z to be equal to a plus bi. A is our real part, right? So we cannot have a to be something imaginary. We know that a has to be real. So we can ignore this solution, that's wrong, and we can consider a to be 5 and a to be minus 5, right? So now we can find values of b using these values of a. We found an equation for b already earlier, right? B was equal to minus 10 by a. So b is equal to minus 10 divided by a. So when a is equal to 5, we have b to be equal to minus 10 divided by 5, which is minus 2. So when a is equal to 5, b is equal to minus 2. And when a is equal to minus 5, we have b is equal to minus 10 by minus 5, which is 2. So when a is minus 5, b is 2, right? And once again, we know that z is equal to a plus bi, right? We're trying to find values of z. So from these solutions, we see that z can be equal to 5 minus 2i or minus 5 plus 2i. So z can just be equal to plus or minus 5 minus 2i. So these are my solutions. So for the equation z squared is equal to 21 minus 20i, the possible values of z I can have are these. These are my solutions for z.